got a really good question for you. And imagine you're looking at the world from above, looking down at, say, the ground level. And we have two objects, object A and object B, as you can see. Object A decides to walk in a path as shown with the dotted line. And they start here at some initial spot, and then they end up over here, and this is the physical path they took through space. Object B, on the other hand, takes its own path, much more different looking path. It starts here at this initial spot and takes kind of this windy path and ultimately ends up over here at this final spot. And the question I'd like you to pause the video and think about is this. Did one object travel farther than the other? And explain your reasoning. So pause the video, maybe write out a complete sentence or two justifying why you think one of the objects traveled farther than the other. And then we'll have a short little discussion here. Great, so I hope you thought about that. And it turns out that really the question is kind of vague. There's actually two ways to think about this. So you might have realized that and come up with two separate definitions for which object traveled farther and might have seen a contradiction here. So if we look at object A, you might take a look at it and say, okay, well look, it starts here and it ends up over here. So if we measure that straight line, the length of that straight line between starting and final point here, and if I just kind of draw that out, give me 1 second, and I'll do that. So this, if we measure that straight line right there, that's longer than if we measure this straight line. So B started out at some spot, and if we draw a straight line from where it began to where it finished, and we compare the lengths of these two straight lines, we'll see that object A has traveled farther in that sense. That's one way to think about it. Now, can you think of another way to think about it? Well, I hope so. And the other way is to trace out the path and then measure the length of that entire path. Now, for object A, it's still just a straight line. We follow the footsteps, if you will, here, or these dotted lines represent the path. And if we measure that length, it would be the same as this line here. But for object B, if we were to take some type of tape measure or a string or something that could curve around and follow the path of this, so imagine like laying out a string that can bend around and exactly follow this path. So let's do that. I'm imagining laying out this string, okay, something kind of like that. And then if we were to, at a later time, lengthen that string out so it is straight, and that might look something like this. It would be a much longer string. So I'm just taking that thing and lengthening it out here. I'm trying to guess how long that is, maybe something like that, and measure that distance with a ruler or whatever you got lying around. You'd find that that is much longer. So the path taken was much longer here for object B than object A. This is leading us to two ideas that we need to talk about in physics. One of them is called distance, and the other one is called displacement. And I want you to figure out, think for a second, pause the video, which one of these quantities is distance and which one is displacement. I'll remind you of the two. The first one we talked about was the straight line length here. So which one is that? Is that distance or displacement? And then the other one is the length of the physical path taken. So this length versus this length up here. Go ahead, pause the video, and decide which word you think is appropriate for those two ideas. All right, so it turns out that this straight line length here from initial to final, if you were to measure that, that would be the displacement. More technically, it's the magnitude or size of the displacement. We'll see displacement as a vector very soon here. And likewise over here, we can measure that in the same way, just taking that straight line path from start to finish and then measuring how long that line is. Whereas the distance is the length of the particular path, even if it's curved, and you need to measure that with some type of device that can bend around and then straighten that thing out and measure the length of that total path. All right, so this is the difference between what's called displacement and distance, and we'll formally define these things now in language. All right, so here's distance defined well. It's the length in meters of the path an object takes as it moves from some initial position to some final position. This path could be curved, And distance does not have direction associated with it and is therefore what we call a scalar quantity. The key word here is the length of the path taken. I'll give you two examples down below in a second. The variable that we typically use is lowercase d. Sometimes you use an uppercase d as well, but we'll just stick with this for now. And then the unit is in meters, and then the type of the variable is a scalar quantity. It has no direction associated with it at all. So when you write a distance down, for example, here, we might have a distance of 5 meters, and likewise right here, we could travel 5 meters in both cases. Now in the first case, we might travel in a straight line along that path from initial to final, but in this second case over here, we might just go in a circle like that. And if we were to measure the length of that path and then straighten that out, we'd find that it also is 5 meters because I hypothetically chose that. That's kind of interesting because in this first case, we end up at this position over here, and then we end up at a totally different position here, and we have traveled a distance of 5 meters. But in this other example, we start at some initial position, and we travel along a path, and we do travel 5 meters in distance, but we end up exactly where we began at the same final position as our initial position. Pretty interesting, right? So that's going to lead us into the next idea of really what displacement is all about. All right, now displacement is a little bit more technical mathematically, so we want to build up how to work with it properly. And I think these two examples get to the main idea. So imagine we're here at some initial position. Again, we're looking at, say, a view from above, watching maybe a person walk in a straight line here versus walking in a circle over here. And they start at an initial position of 2 meters. Also notice I've chosen just to take the vector symbol notation off for convenience here. Sometimes we'll do that. But we have an initial position of 2 meters, and we walk along this path, and then now we're here at a final position of 5 meters. By how much have we been displaced? We started at some initial position, and then we have become displaced a certain amount. How much? Maybe pause the video and think about that. All right, well, hopefully you can easily see that if we started out at an initial position of 2 meters and walked in a straight line to the right, we've changed our position by positive 3 meters. We have been displaced from where we originally started by plus 3 meters. That's how you go from 2 over here to 5. Now, importantly, if we had been displaced by negative 3 meters, what do you think would have happened? Well, we would have decreased our position, so we would have gone from 2 meters to the left and finished at a position of negative 1 meter. All right, so that's a simple example in a straight line for thinking about displacement. What about over here? What about if we start here and we walk around in a complete circle? We take one trip around this circle and then we end right where we began. What do you think our displacement would be then? Pause the video and think about it. Well, if we started and stopped in the exact same position, we wouldn't have been displaced at all. That's kind of what the word displaced means in our everyday, but we'll make a better technical definition of it here for physics in just a second. But we can see we start at this position and we end at that position, and so we haven't been displaced at all, even though we certainly traveled a lot of distance to go around in that path. So the displacement is the change in position of an object. The magnitude of the displacement is the straight line distance between an initial and final position. And to calculate the displacement of an object, we just subtract the initial position from the final position. However, please remember that position in physics is a vector quantity. So we actually have to use the rules of vector subtraction to calculate any displacement correctly. Now again, we'll see in one dimension when we're moving along a straight line, it'll end up being exactly the same as just adding and subtracting numbers like normal because of the way one-dimensional math works with vectors. But when we get to 2 dimensions, then we have to be very, very careful that we're subtracting 2 vectors from each other, as we'll see. Now this is a good opportunity for you to practice turning language into a mathematical equation. So right here, to calculate, subtract the initial position from the final position, remembering that position is a vector. I'd like you to come up with a mathematical expression now for displacement. So displacement is the change in, that's what the delta symbol is, change in position x, and that position is a vector quantity. So we have change in some vector quantity called position. Finish the equation here. What would go next? Pause the video and try it. All right, well, you saw there was a subtraction, so we have to have a minus sign. And what are we subtracting? Well, we're subtracting an initial position from a final position, and we know that positions are vectors. So here's our initial position. It's a vector, and we're subtracting that from a final position. So anytime we see this delta symbol over here, again, that means change in some quantity, we notice a subtraction comes up. And it's a subtraction between a final and an initial. So here's a simple little check for understanding to make sure you can do this. Here's a coordinate system. We start here, some person is at position x is equal to 3, and then we move over, we travel to the left, and we end up over here at a position of x is equal to -1. I'd like you to draw the two position vectors, so the initial position vector and the final position vector, and then use vector subtraction to calculate what's called the displacement vector. Remember that displacement is a vector. So how can we construct that vector that represents it? Now go ahead and try that. You might have to, if you haven't done so, watch the video on position and position vectors. So pause, think, and do some physics here. Okay, so number one, draw the two position vectors. Remember how we do that? We start at the origin, and then we draw an arrow over to the first position. So that arrow would have a length of 3, or a magnitude of 3, and it would be pointing to the right. And I've drawn it over here. So this is the initial position vector as represented by that arrow. The final position vector, same process, start at the origin, draw an arrow to the final position, that points to the left, and it only has a magnitude of size 1. So we have our initial and final position vectors drawn. Now we just have to subtract them. And I'm also representing that symbolically here by saying the displacement vector is equal to a subtraction between these other two vectors that we've just drawn up here. Okay. So go ahead now and use the rules of vector subtraction, draw it out graphically to show what the displacement is. All right, hopefully you got an answer, and let's see how to do it. So the first thing we have to do is draw the first vector in the subtraction here, which is actually the final position. So we'll draw that one out first. There it is. Has a length of 1. Be real careful to make sure we get that sized correctly. Okay, now we use the tail to tip method. So we'll take the tail right here of the next vector and put that onto the tip of the vector we've just drawn down here. However, we got to be a little bit careful because when we subtract two vectors, we have this minus sign out here, and we need to remember what that does. It flips a vector around 180 degrees. So to minus the initial position vector, we actually have to draw we have to rotate it by 180 degrees. So it's going to be pointing to the left. Okay, so when we end up doing that now, I'll draw that here. And so to be technical, we've got our final position vector there, and then this one is minus the initial position vector. And all we're doing is adding those two things together with simple vector addition. We're going from where we began, where we started. I'll just draw it above the line so we can see it. And then we're drawing a straight line like this to where we finished, just like we always do. Start, finish. And if we measure the length of that line, then we'll be able to get the answer. And if we also put the magnitudes here, so this had a magnitude of 1, and that had a magnitude of 3. If we just visually look at that, we can clearly see, since it's all along a one-dimensional line here, we can see we just add 1 to 3, and we get, well, we get a length of 4, but we need to be a little careful because which way does this vector point? Well, this vector is pointing to the left. So if we were going to write out the final answer, it would look something like this. The displacement of this object now would be minus 4 meters. And this minus sign is telling us that this points in to the left. Okay, so points in the negative direction. Very important idea, because if you could imagine us being displaced 4 meters to the right instead of to the left, well, maybe there's some cliff here or something, right? And if we said, hey, displace yourself positive 4 meters, well, that would not be so good right there now, would it? But being displaced negative 4 meters here, now you're on solid ground. So the direction of the displacement totally matters, obviously, when you're working it out. Now that process that we just went through, that would also work for two-dimensional vectors. So maybe if one of these vectors over here was rotated in the second dimension, we would follow the same procedure. We would just subtract them like we've seen before with vector subtraction, and we'd draw a resultant vector, and it would end up being probably at some angle. Okay, we'll get there when we get to two-dimensional motion more specifically. But I do want to point out that when we are working in one dimension and we're doing these displacements and these subtraction problems, this notation here with all of these vector symbols above the quantities, it can get a little cumbersome. It can look visually intimidating, especially when you're first learning physics. So we tend to kind of drop all of these vector symbols sometimes when we're working in one dimension and even two dimensions, as you'll see as we move forwards. To do this thoroughly, we do want to use it so we can technically show you the exact right way to do things. But now I'm going to go ahead and just drop that vector notation and just write the displacement like this: final position minus an initial position. That's how we calculate a change in position. And as long as we're in just good old one dimension, we can just use numbers like we're used to doing in math. So for example here, we have a final position of 1 meter, and then we have, I'm sorry, that is wrong. We have a final position of minus 1 meter, and we have an initial position of 3 meters. So if we subtract those two together, we get an answer of minus 4 meters, and then we're done. Something kind of like that, which is exactly the same answer we got over here through the vector math, where we were really careful to remember that positions are actually vectors. Okay, so a little helpful simplification when we are working in one dimension, but in the back of your mind, you should be aware that these are vectors, and we can use this little trick because we're in one dimension. Oops. All right, let's wrap this video up with one more example for you to work on, and then I'll show you one more cool thing about displacement that I think you'll like. So here's a problem. We have a person, they begin at moment 1, and then they just start walking along the number line in some fashion. At some later time, moment 2, we see them here, and then at some final moment in time, we see them over here at moment 3. Okay. Here are the positions, x1, x2, and x3 labeled. I'd like you to calculate the displacements between positions 1 and 2, 2 and 3, and then finally between position 1 and 3. Go ahead and give it a shot. Since we're in one dimension, we don't have to really draw any vectors at all. We can just work with the numbers and plug it in here. Notice the little notation I like to use is going from position 1 to position number 2 with this little arrow over there. That symbolizes the initial position and then the final position right here between any two particular moments you're interested in. All right, so you plugged it in. And position number 2 is negative 3 meters, and position number 1 is 2 meters. And when you get that, that ends up being minus 5 meters. All right, so we started here, position 1, and we walked all the way over to position 2, and we can see we've been displaced by negative 5 meters. Negative 1, negative 2, negative 3, negative 4, and negative 5. Makes sense. We've changed our position by negative 5 meters. Next one. So let's take a look here. We have position 3, which is 1 meter. And then we need to minus, and be careful here, position 2 is a negative 3 meters. So those two minus signs become a positive, and we actually get plus 4 meters. Great. So we'll double check that. And here we are at position 2. And we end up here at position 3. And we've changed our position by plus 4 meters. So we start here 1, plus 1, plus 2, plus 3, plus 4 meters. Awesome. Also remember, we are in one dimension here, so we can just do simple addition and subtraction with numbers without having to get bogged down by all that vector notation and drawing the vectors. All right, so I've drawn, or I've written out the last one, and it is minus 1 meter. So if we didn't really care at all about any of the motion, and except for where we started and where we ultimately finished here between moments 1 and moments 3, we would have found that we would have been displaced to the left, or negative 1 meter. One final thing I can do here is actually just draw some displacement vectors kind of by the number line. So if we draw the first one from 1 to 2, well, we just go from where we started to where we finished. There we go. And that would be the displacement vector from 1 to 2. And it has a length of 5 meters, and it's pointing in the negative direction. We could also do it from 2 to 3, so I'll kind of go up here just to get it out of the way of the other one. So we begin here at this location, and we end up over here. And so that would have a length of 4, and it's pointing to the right in the positive direction. And then finally, we could also do this one right there, that displacement vector, starting at moment 1, ending at moment 3, and it is pointing to the left and has a length of negative 1 meters. Now, one final note here, just to kind of zoom out and take a little bit more abstract view of what's happening here with displacement vectors, to be specific. Let's look at the formula, right? The change in position, which is displacement, is a vector, and it is calculated by subtracting two position vectors, an initial position vector subtracted from a final position vector. But if we play around with the math a little bit, just doing a simple algebraic step, by solving for the final position vector, writing that over on the left, see if you can figure out what goes here on the right-hand side from this equation above, and interpret what you're seeing. See if you can make it make conceptual sense to you. I think you can if you just think for a second. Pause the video and try it. Okay, well, hopefully you're able to just do this simple algebra here, and you can see by bringing over this minus initial position to the other side, having it become positive, we get that the final position vector is whatever the initial position vector is. We'll add to that some displacement, some change in the position, and we'll produce the final position vector. Now, what if we have no change in position? What if our displacement was actually equal to 0? Well, that would go away, that term over there on the right, and then we would have a statement that hopefully makes sense to you. It says that the final position vector is identically equal to the initial position vector. Hasn't changed at all. It's the same vector. That should make sense if we have had no change in the position at all. So to complete the picture, let's draw all three of the vectors on this diagram up here. We start at an initial position of negative 1, and then we walk to the right, and then we end up at a final position of positive 2. So pause the video and draw each one of these three vectors. The initial position vector, the final position vector, and then the displacement vector. And then we'll add them together using vector addition, showing that if you add the initial position vector here to the displacement vector, you'll produce the final position vector. Give it a shot. All right, so I've drawn all three. Remember, we start from the origin, we go out to a position to find individual position vectors. And then remember that displacement, by definition, the magnitude of displacement is the straight line distance between an initial point and a final point. So here is that straight line distance. You just draw a straight line, but then you have to give it some direction, because obviously that matters if you're displaced positively or negatively. So here, if we start initially on negative 1 and we go to positive 2 over here, we've been displaced to the right. All right, so we now have all three of our vectors. I'll even write delta x here. Okay, perfect. Great, so now all that's left to do is just do the addition. We'll write out the first vector, which is the initial position vector. So I'll just do that, I guess, over here on the right-hand side. So there's my initial position vector. And then I'll add to that my displacement vector. So I'll use the blue color just to be consistent here with the one I have up there. And we'll label these. So here's my initial position vector, and then I'm adding to that my displacement vector. And then I do what is always done. We go from where we began to where we finished. And I'll do this, I guess I'll just choose one final color here. I'll do this in red. So we started here, and then we ended over here on the right. So this would now represent our final position vector from that vector addition of adding the initial position vector to the displacement vector. Great. So there you have it. A full view of distance and displacement with all the technicalities to be correct with the vector math. Also seeing how we can loosen those restrictions here a little bit in one dimension to make our lives a little bit easier, but then coming back at the very end and seeing how important this concept was of working with vectors, because we can abstractly see how creating a final position is just a vector addition between an initial position and some displacement using vector math. All right, fun stuff. We'll see you in the next video.